In the last video, we introduced the idea of a surface integral, found that it was a very complicated looking integral, but that it was easy to compute as long as I could find a parameterization for the surface sigma that I was integrating over. This allowed us to convert the entire integral into a double integral over the UV plane. So let's go ahead and take a look at an example of putting this to use. Let's take a look down here at a surface that I have a picture of over here on the side. And this surface is the surface sigma. According to the set notation that we have in example 1 here, I have this surface is given by the formula y equals 2x squared plus 1. Okay, so this is kind of like a parabola-like shape here. You could actually see that my parabola shape could probably be extended. Right? And I can kind of imagine it going off like this. But I have this parabola-like shape, but I'm only graphing part of it. I'm only graphing it on the range where x goes from 0 to 2. And it has some height distinctions here where z only can go from 4 to 8. So if I wanted to do a surface integral for this particular surface, okay, if there was some quantity I wanted to add up over that surface, one of the first things I would have to do is find a parameterization for this. Now, finding a parameterization here is actually super simple to do because I can quickly see that there's already a given relationship between the x and the y variables. So I'm going to go here and let my x just represent the variable of u. Okay, so x here is going to play the role of u. And if that's the case, that would mean that y is equivalent to 2u squared plus 1. But what in the world should I make v? Well, note here that what should I make v, or what should z be equivalent to? And what you'll notice is that my z variable actually doesn't seem to really have any interaction or any direct relationship to the x and y variables that I have. And so this makes it a perfect selection to just say my z variable could just be represented by v, okay, that z component. Of course, here when I'm doing a parameterization, I also want to state some restricted ranges on my variables of u and v. Well, note here v is super easy. I have that v here is equivalent to my z variable, so if z goes from 4 to 8, v should also go from 4 to 8. Similarly, x is playing the role of u, and since x goes from 0 to 2, u should also go from 0 to 2. So I have a perfect parameterization here, and this should make it really, really easy to evaluate in part B this surface integral. Okay, if I want to do this, the first thing I should note is that I've been given right here my function of f of x, y, z. This is the formula that's kind of telling me what I'm adding up as I traverse along the surface. Now, I don't know if this is supposed to represent an electrical charge or gravitational forces or some amount of fluid flow, or I'm not sure what it represents, and that's actually not really important for calculating the surface integral. It would only be important for interpreting the result. So let's just see how I go about the calculation. What I would want to start with first is identifying everything that I had needed to set up the integral over here at the right. What I'm going to need is a parameterization, which I already have, so that way I can update my function f. But I'm also going to need this cross product of the partials of r being normed. So let's actually go ahead and start there. So I'm going to go ahead here and quickly start by saying that I can note that RU cross RV should be equal to, and I'm going to get ready here to set up my cross product. Okay, so remember that RU is what I'm going to place, or partial of R with respect to U is what I'm going to place here along the top. It looks like my partials for each of my components are going to be 1 for the first component, 4U for the second component, and 0 when I do the partial of V with respect to U. Similarly, now when I go through and I do the partials of each of my components with respect to v, I'm going to get 0, 0, 1. So this is actually going to be a super easy cross product here to calculate. Keep in mind, when I do this, my middle term is going to have a negative on it. And let's see what I get here. So for my middle term, I'm going to be doing, looks like 1 minus 0. And for my final component, it looks like I'm just going to end up with 0. You can double check my work there on the cross product, but we've done tons of these in the past. I should end up with a vector that looks like this. Now I need to go ahead and actually calculate the cross product here, or sorry, the norm of the cross product. And I can see that that's going to give me 16u squareds plus 1. Okay? So now I should be able to go ahead and actually fully set up this integral. So it should be the case that the integral that I started with should be able to be rewritten as, let's see, I'm going to update my function first. My function here is x and then z squared. So I note up above that my formula for x, my formula for y, and my formula for z are all given in my parameterization. So I'm going to end up with here u times v squared. And then remember, in place of ds, I'm going to be putting down my norm of my cross product, and then multiplied by dA. Now I'm integrating over the region that's given to me in the UV plane. But fortunately, I can see from up here that this is where D is communicated. So D is communicated here. I can see already what the range on U and V are. Apparently, I'm integrating over some rectangular region. So I'm going to go ahead and put the U variables first and the V variables second. This doesn't change anything about my integrand. And then my differentials at the back would just be du dv. And boom, I'm ready to go. Okay, so I'm actually going to go ahead and pause here. I'll leave it to you to actually go ahead and attempt to compute the integral on your own, as I want to focus a little bit more on just the setup of these integrals. You can, of course, go ahead and look at the full notes to see exactly what the integral and how I got to the final answer for the integral. This, though, is what the final result ended up being if you were to go and compute it yourself. Let me just zoom out here slightly. So I ended up with 65 to the 3/2 power in there, minus 1. So hopefully this gives you an idea of how exactly I can go about evaluating or setting up one of these surface area integrals.